and that, and this. And guys, today is the 7th. The topic for your notes today is nuclear chemistry. And guys, we are going to start by going over all of the homework. So, regardless of what you've got on your homework page, this is the stuff that you need to know specifically for the test that you have, not next Wednesday, but the Wednesday following. You guys ready to go? Okay, so do this, guys. Draw these 5 atomic models. Make them about, 4 or 5 centimeters, 2 inches across. Spread them out across the page. But guys, when you then skip down to do the bottom 2, leave yourself 5 lines of space between the top row and the bottom row. And we are going to talk about everything that you need to know about these researchers and what they figured out about atoms. Have any of you actually had teachers that have told you have a sub tomorrow, go get them? I actually have heard that here. I figured you guys probably didn't have those teachers because you're also not that kind of student. But brings up some interesting thoughts about segregation in schools. Never mind. You guys all caught up? What if we all wait to draw Schrodinger's model till the very end, and then we can all draw it together, and when we draw the little dots, it'll sound like it's raining? Yes. It'll be magic. Kind of like EFY, those silly that you do. Right? Do you guys do that? Where you rub your hands together, and then it sounds like it. Yeah, all right, never mind. Guess that was just me when I went to camp. Boy Scout camp? You do it there? You guys know what I'm talking about? Where you're all around the campfire and you snap your fingers and no, all right. You've done that. No? I thought you were raising your hand, Zach. Never mind. I'm digging myself a pit. I'm going to shut up now and let you guys draw. Are you guys done? All right, everybody draw the dots. You ready? By the way, guys, disturbing thought. What do those dots represent that you're drawing? The answer is not electrons. The answer is one electron existing in multiple locations simultaneously. We'll talk more about that in the next unit. See? I told you. It's magic. Good heavens. All right, you guys ready to go? So, guys, I know that a lot of you have a lot of different things in terms of the things that you gleaned out of those websites as you were gathering information. Guys, bottom line is, here's what you gotta know. Now, guys, let's make the connection first. As you were drawing these atomic representations, you should have had this experience of, oh my gosh, I've drawn these before. Because, guys, if you allow your eye to scan down the right-hand column of your homework, by the way, don't put your homework away. If you allow yourself to scan down the right-hand column of the homework assignment, you'll notice that these are the atomic models that you should have drawn from first Dalton to last Schrodinger. So, guys, what I'm going to do is I'm going to distill this for you into what you need to know about these, not just atoms, but the people that came up with it. So, guys, first of all, this, John Dalton. And, guys, John Dalton, who was a Brit, did any of you catch the date by any chance? Was it 18-something? Do you know, Ryan? No, 1803. So early 1800s, right? By candlelight. So this is 200 years ago. So guys, 200 years ago, you don't need to know dates, but guys, 200 years ago, a guy named John Dalton studied gases, which if you think about it is sort of amazing in and of itself. If I were to set you out right now and go, okay guys, collect some gases and study them, most of you would give up just trying to collect gas. But once you collected the gases, then Dalton started studying these systems. And what he did is he made some fundamental observations about the nature of atoms. Now guys, here's the trick. So they came up to Dalton then, and said, hey, John Dalton, gosh, great chemistry. So what are these little things called atoms like? And so John Dalton was trying to come up with an analogy for what atoms were like. And so Dalton thought they were like pool balls. Have you guys all played pool? Rack them up, 8-ball, cue ball, break the rack, pool balls. So Dalton imagined that atoms were these little dense permanent balls. But instead of calling them pool balls, because he's a Brit, in Great Britain they don't play pool, they call it billiards. And so if you think of billiard ball, think of pool ball, and that's what John Dalton thought atoms were like, were these little small dense permanent balls that he described as pool balls. Get the idea? You're good on Dalton? Okay, so now guys, fast forward 100 years. For all of the 1800s, we thought atoms were little itty bitty pool balls. Well then guys, along comes a dude named J.J. Thomson. And J.J. Thomson carried out some experiments with the thing that we'll look at in a minute called the cathode ray tube. So what did he discover? Well, he discovered the electron. Guys, understand this was groundbreaking because it showed that Dalton was wrong. Dalton thought that atoms were indivisible. And along comes Thomson and he says, no, actually atoms are made of things, which was crazy groundbreaking. And so guys, when they went to Thomson and said, all right, Thomson, what is an atom like? Well, guys, understand that Thomson was also a Brit. And this was his thinking. So Thomson discovered electrons, but he was smart enough to understand that if electrons are negative, there's got to be something that's positive. You can't have one without the other. So he described an atom as being a big old ball of negative goo with these little positive things floating around in the goo. Well, the best analogy that he could come up with as a Brit was pudding, and not just any pudding, plum pudding. So Thomson said atoms are like little balls of plum pudding where you've got the negative goo and then the positive plums floating around inside the pudding. Get the idea? Okay, so how did he come up with this? Well guys, this is actually what a cathode ray tube looks like. You've got a battery, and guys understand Nicholas Volta about 30 years before this invented batteries, and he understood that batteries actually take atoms and pull them apart. And what he found out was if you could take this battery and hook it up to a cathode ray tube, which is essentially just a vacuum tube with a gas in it that glows when things go through it, what he found was that this beam would travel from one end to the other. And guys, he knew that this beam was made of the parts of atoms. The smart thing that he did is he put a magnet near this, and the magnet made the beam bend. What did that tell him about the beam? It was charged. So guys, he proved that there were these negatively charged particles inside atoms, and he called them electrons. You get the idea? Okay, so there's Thomson. So then guys, after Thomson, we do not make the jump to this model. Whose model is this? Flip your page over. This is Rutherford. But guys, it turns out that between Thomson and Rutherford, we have our good friend Robert Millikan. Now guys, Millikan does not have a model of the atom associated with him. The nice part is he did get a Nobel Prize for his research, he just didn't get his own model. And guys, it's actually really cool. Millikan did this research at the University of Chicago. You can go to the University of Chicago and his oil drop experiment is still set up. It's still sitting there. You can go tour it. It's really cool. Anyway, so what Millikan did by doing this thing called the oil drop experiment is he figured out the charge of an electron. Not that it was negative. Thomson figured that out with a magnet. Millikan proved how negative it was, and he quantified the charge of an electron. What do we know the charge of an electron to be? -1. And he's the one that assigned that 1 to it and figured out what the number was. But we don't associate a model with him. You guys good there? Okay, so now guys, you can flip your page over, and we are ready to talk about our good friend Ernest Rutherford. So now we're back over in Europe. And guys, this is how this went down. So this was like 1920s, I think. So prior to Rutherford coming along, we thought atoms looked like this, just a big jumble of positives and negatives. Well, guys, Ernest Rutherford did this thing called the gold foil experiment. And when he did, he figured out that Thomson was wrong. That in fact, the positive plum pudding plums are actually not spread uniformly throughout the atom. They are actually clumped together in the middle of the atom. And what do we call that clumping together of the protons in the middle? The nucleus. He discovered the nucleus of the atom. And he not only discovered that atoms have a nucleus, he discovered that in that nucleus, that's where the protons are, because he figured out that the nucleus was positive. And so guys, we call this the nuclear model of the atom. How you doing? You guys all caught up? Can I go on? Okay, so guys, how did he do it? Well, this is what the gold foil experiment looked like. What he did is he took a chunk of radioactive material. Think uranium. And by the way, guys, I may as well just tell you right now, this is a chunk of uranium. We're going to play with this later. But imagine and he didn't use uranium, he actually used radium, but he stuck a chunk of radioactive material inside of a box, a lead box. And then he poked a hole in the side of this lead box, and it allowed this beam of radioactive particles, called alpha particles, allowed this beam of alpha particles to come shooting out of the box. Then what he did is he shot that beam of radioactivity at a piece of gold foil. He literally took a piece of gold and hammered it flat like aluminum foil, and then he surrounded it with a detector. Now guys, this is what he found out. Most of the alpha particles went straight through the gold. And guys, I'll tell you what to write down, but you want to write these things down. So guys, most of the alpha particles went straight through the gold foil. What does that tell you about atoms if you shoot stuff at it and most of the stuff goes straight through? They're mostly empty space. Guys, include that in your notes. Rutherford found out that atoms are mostly empty space. How much empty space do they have? Remember our analogy? If the nucleus is the size of a marble, the atom's the size of Lavelle Edwards Stadium, and the only thing inside the atom is the nucleus and the electrons are around the outside. They're mostly empty space. Then the other thing that he discovered was this. So some of these alpha particles hit the gold foil and bounced straight back. Now guys, what would happen? So imagine my fist is an alpha particle, and here's the gold foil, and most of the alpha particles went straight through. But imagine that an alpha particle hit and then bounced. What must have happened to the alpha particle? It hit something. We didn't know it was the nucleus yet, but it hit something. And what has to be true of the something that it hit? It's got to be really dense. Because guys, what if the nucleus wasn't that dense? Well, the alpha particle would hit it and still keep going. So guys, Rutherford found out that these nuclei are like brick walls. You hit that and you're bouncing back. So the second thing that he proved was that nuclei are dense. That's number 2. And then guys, finally, how did he prove that the nucleus was positive? Well guys, check this out. Imagine that my hand is the nucleus of an atom. Oh, you're still writing. Guys, imagine my hand is the nucleus of an atom, and imagine my fist is an alpha particle. Now let me let you in on another secret. Alpha particles are positively charged. So guys, here comes this alpha particle. If it misses the nucleus, it goes straight through. If it hits head on, it bounces off. But guys, what if it only comes close? Now this is positive. So if this comes like this and it bends away, and some of these alpha particles did that, it bent away. So if the alpha particle is positive, what does that tell you about the nucleus if the nucleus causes it to bend? the nucleus is also positive. Like have you ever done this? Tried to stick two north poles of a magnet together and they just run past each other? Well, guys, it turns out that charges do the same thing, and because some of these particles bent, he found out that they're positively charged. Get the idea? Okay, so 3 things about Rutherford. Atoms are mostly empty space, atoms have a dense nucleus, and the nuclei are positively charged. You guys good? Okay, go on. All right, so now, guys, we're down to the bottom. So here we go. So after Rutherford, we understood that there was a nucleus. But guys, check out the electrons in Rutherford's model. What do they look like? Thomson's model. They're still all mucked together. They're still plum pudding. The only difference is that Rutherford put all the plums in the middle. They're still pudding. Well, guys, it turns out that it took a guy named Niels Bohr to finally come to understand partially what the electrons are doing. And guys, here's what Bohr did. And we're going to do this in lab in the next unit. What Bohr did is he took atoms and he passed energy through them. And when he passed energy through these atoms, he found that they emitted light. So Bohr studied light. And by studying the light that these atoms released, he figured out that the electrons are not just jumbled around like pudding, they are actually organized into orbits. And guys, this then became what's called the planetary model, because Bohr thought that atoms are organized like our solar system, where the nucleus is the sun and the electrons are like the planets. Get the idea? Okay. Now guys, here's the thing that's interesting and disturbing. If I were to ask you right now to take your paper, flip it over, and draw for me an atom, this is what almost all of you would draw. You guys actually believe that atoms look like solar systems, where you've got the nucleus and then the electrons move around the nucleus like planets around the sun. And guys, that could not be any more wrong. But why do people teach that? Well, guys, in biology class, that's good enough. In junior high science, that's good enough. Well, guys, it turns out that while it's good enough for some, it's not good enough for a chemistry class. Guys, this is what atoms actually look like. Kind of. So let's talk a little bit about this. Guys, this was a model that was developed by a guy named Erwin Schrödinger. You're going to find out in a video that we're going to watch in a couple months. Schrödinger was a really brilliant guy, but he was a slimy dude. He actually came up with this model for an atom while he was hiding from his wife, having an affair at a hotel up in the Austrian mountains. He was a slimy guy, but he was also a really good scientist. But guys, this is what Schrödinger did that made it really kind of interesting and unique. He began to believe that Bohr's model was not correct, that these atoms, these electrons, were not spinning around the nucleus like planets. The problem is he couldn't come up with experiments to prove it. So instead of doing experiments, he did math. So guys, he is the first computational chemist. He didn't do any experiments. He did math. And when he did this math, he figured out that electrons do not move like planets. They move more like waves. And he called this the wave mechanical model of atoms. And so we call that model the charge cloud model of an atom. These electrons do not move like planets. They behave more like waves, and these waves look like clouds, and we call it the wave mechanical cloud model of the atom. Now, guys, understand, when he proposed this, people hated it. Most of all, Albert Einstein. Einstein hated Schrödinger. They actually just about threw punches. If you can imagine Albert Einstein with his hair all freaked out, ready to go. But guys, they hated each other because Albert Einstein, who was very much a believer in practical physics, thought that Schrodinger was like unto Satan because he couldn't come up with experiments to prove what he was saying. All he had was math. And certainly Einstein was good at math, but he didn't like math that you couldn't prove in a lab. And the problem is that when Schrodinger came up with this, it was just so long ago, we didn't have the ability to do the right experiments. But as we've been able to do the right experiments, it turns out Schrodinger was right and Einstein was wrong. Yeah, it's interesting. Imagine being smart enough to prove Einstein wrong. But it happened. All right. So, guys, zooming back out, how you doing? Anything there you want to talk about relative to your homework, relative to what you just learned, or the understanding that you're going to need to know these 4 things for each one of these experimenters on the test? You guys good? You're okay? All right. So guys, then we're going to shift gears, and here's what we're going to do. We are going to spend the rest of this unit talking about the nuclei of atoms, okay? That is our purpose for 2 days of lecture and 2 days of videos and paper writing. We are going to talk about the nucleus of an atom. So guys, you can just slide your homework to the side. We're done with that, and it's time to start talking about the nucleus. Still the same notes, you just don't need your homework anymore. Okay, so guys, if we're going to talk about the nucleus, we need to identify, guys, and you don't need to write. The next 3 or 4 slides are just review. Guys, we've already talked about the nucleus. So let's review what we know about the nucleus. You ready? First of all, we encountered this image in one of our videos, and we found out that the nucleus contains protons and neutrons, and then the electrons we now know are not orbiting around the nucleus, but we'll deal with the electrons after this unit's over. So we understand that about the nucleus, protons and neutrons. And then we talked about some ridiculous ideas. Remember Jumpsuit Boy? A little disturbing. Guys, we learned that the nucleus is ridiculously small. That if you blow up an atom to the size of Lavelle Edwards Stadium, how big is the nucleus? A marble. It is ridiculously small. But most of the mass of an atom is in the nucleus of the atom. Most of the mass is in there. So we talked about this idea that remember our box. If we wanted to take a 1-foot box and make the matter inside of it as dense as the nucleus of an atom, what would we have to put in the box? Remember? Cars. How many cars? 6.2 billion cars. So guys, if we want to create matter as dense as the nucleus, we have got to stick 6.2 billion cars in there. Remember that idea? Okay, so we know the nucleus is dense. We know the nucleus is small. But guys, now you know something else about the nucleus. Who discovered it? Who discovered the nucleus of the atom? Guys, if you don't, Rutherford discovered the nucleus of the atom. Now guys, here's the thing you got to understand. When Rutherford discovered the nucleus of the atom, and how did he do it? Gold foil experiment. He published a paper. And he said, hey, science world, I just did this gold foil experiment, and guess what I just found out? I found out that Thomson was wrong. The electrons are not like little plums in pudding. All of the protons in an atom are clumped together in the middle of the atom. And when he published that paper, he was treated like an idiot and asked to leave the scientific community. They thought he was an idiot for proposing that an atom would have a nucleus. Now guys, the question is why? Why would proposing that the atom has a nucleus that's full of protons, why would that idea be absolutely ridiculous to anybody that knows anything about science? And I'll just be frank with you guys because I know you can take it. I was a little disappointed because every year I have students in my classes, when I tell them that the nucleus is full of neutrons and protons, every year somebody raises their hand and they go, no, it can't be. There can't be a nucleus in an atom. Somebody in every one of my classes picked up on this. You guys didn't. So we need to talk. So guys, let's talk about what we're talking about. I just picked potassium. So guys, this is the way we represent atoms. We know that the nucleus is full of protons and neutrons. We know the electrons are around the outside. Again, this is sort of Rutherford's idea. But guys, when Rutherford told the world that an atom has a nucleus, they thought he was a fool. Why? Yeah. Why? Why? Yeah, guys, did any of you pick up on that and just not say anything? Guys, what is the charge of protons? They're all positive. And guys, positive charges do not attract each other. What do? They don't want to be near each other. It's like two north poles of a magnet. They don't want to be near each other. They want to be away from each other. So when Rutherford said, hey, yo, the nucleus is made of protons, everyone went, because we know enough to know that positive charges do not attract, they repel, and there's no bloody stinking way on earth they're going to clump together in a ball. But Rutherford stuck by his guns and said, oh yeah, this happens. I can't explain why, but it happens. So guys, then years and years later, we figured out why. Do any of you know why? Guys, what is it that allows these protons to clump together? And the answer is not neutrons. What is it that allows them to clump together? Do you know? Interesting idea. Could it be the electrons? But guys, the electrons are negative. And what do positives and negatives do to each other? They attract. So if anything, the electrons are pulling on the nucleus and trying to pull it apart. Do any of you, if you don't know, you just don't know. Do any of you know what it is that allows the nucleus to exist, the protons to clump together? No? Then I'll just tell you. Guys, it goes like this. There is a force. That's all I could come up with for force. But guys, there is a force that holds the nucleus together. And this force is not gravity. And this force is not magnetism. There is another force in the universe, and the only purpose that this force has is to hold the nucleus together. Do any of you know the name of the force? It's not a very creative name. It's actually called the strong nuclear force. You want to write this down. So guys, the strong nuclear force is the force of attraction that holds the nucleus together. And again, why does the nucleus need held together? Because it doesn't want to be together. Like Mary said, these positives, the protons, are pushing on each other. They don't want to be together. They want to be apart. But it turns out there's a force in our universe that overcomes that. Rutherford didn't know it existed, but thank goodness he stuck by his guns and said, I can't explain it, I just know it's there, and we'll let people later figure out how it happens. And guys, later they named this force the strong nuclear force. Now, guys, here's the $11,000 question. How strong does a force need to be to keep protons together? Well, you ready for the sobering answer to the question? If you break this force, it releases enough energy to level cities in Japan. Guys, when we dropped that bomb on Hiroshima, and then later when we dropped another bomb on Nagasaki, all of the energy that leveled those cities, guys, simply came from breaking the strong nuclear force. Because when that strong nuclear force breaks, you are releasing the strength of that force. And guys, it is enough energy that a very, very, very little bit of matter, like less than a gram, and guys, did you know that? When that bomb went off over Hiroshima, less than a gram of uranium got broken apart. Less than a gram. That's a paper clip. Guys, less than a gram of uranium broke apart, but by breaking the strong nuclear force in less than a gram of uranium, it was enough to level the entire city of Hiroshima. Isn't that crazy? Guys, you've got to understand that this strong nuclear force is strong in a way that you cannot even comprehend. Get the idea? Okay, so guys, this is what we're going to do today. Don't write this down. This is our overview for today. Guys, now that you understand that the strong nuclear force exists, we are going to talk about how it changes. And guys, this can happen in one of two ways. This can happen in high energy ways, and this can happen in low energy ways. And we are going to talk about both. Again, you don't need to write this down, but this is our marching orders for the rest of the today. So guys, when the strong nuclear force breaks apart in a high energy way, these are processes called fission and fusion. But it can also break apart in low energy ways, and this is what we call radioactive decay. And you're going to find out that you are going to learn about 3 different types of radioactivity: alpha, beta, and gamma decay. This is not the whole list. There's about 15 or 20. You only need to know 3. So guys, this is our overview for the rest of the day. When the strong nuclear force breaks, it can do it in high energy ways, fission and fusion, or low energy ways that we call radioactivity, and we're going to go over alpha, beta, and gamma, which conveniently are the first 3 letters of the Greek alphabet. You guys ready to go? One at a time. You're good? All right, here we go. So guys, first of all, fission. High energy change. Scratch this in your notes. So guys, what is fission? Oh, are you going next door? You're welcome. So guys, nuclear fission is a nuclear process where the strong nuclear force breaks and atoms literally split apart into 2 smaller atoms. The thing that's cool is when they break, you don't get a little atom and then a bigger atom. Then they break almost exactly in half. It's really interesting. But guys, when nuclear fission happens, what we have taking place is we're taking bigger atoms and we're making them smaller. So guys, here's the interesting question then. Where in our universe does nuclear fission take place? Do you know? Not stars. That's fusion. That's the opposite. We'll talk in a minute. Where does fission take place? You guys ready for a weird thought? Guys, the only place that nuclear fission takes place is here on Earth. And why does it happen here on Earth? Because we're here on Earth. Guys, nuclear fission only takes place because we make it happen. Now, the question then becomes, where is it that we make it happen? Where on Earth right now is nuclear fission taking place? Do you know? 2 places. One of them is in nuclear power plants. Most of our nuclear power plants are on the East Coast. On Tuesday, you're going to find out that there is one nuclear power plant west of the Mississippi. It's over in Washington, and Bill Nye is going to take you on a tour of it. Guys, don't think Bill Nye is, Bill, like 3rd grade Bill Nye. This is actually Bill Nye for grown-ups. It's called Eyes of Nye. It's really fascinating. But guys, this is the process that is taking place inside of nuclear power plants all around the world right now. France is coated with nuclear power plants. 90% of their electricity is generated by taking uranium atoms, breaking them apart, and getting the energy out. But guys, where else is nuclear fission taking place right now? Frighteningly, the answer is North Korea. Guys, North Korea is the only country in the world right now that is actively detonating nuclear weapons. That dude is nuts. I don't know if I can actually, I think it's actually, you can say that and it's not an opinion. I think they actually have, it's Kim Jong-un, is that his, I think they've actually diagnosed him as being crazy. But whatever's going on here, guys, North Korea is actively in the process of detonating nuclear weapons. Who knows what his intentions are? But guys, the interesting part of this is you've got to understand that no matter how crazy this North Korea dude is, there's only one country in the world that has ever used nuclear weapons against people, and that's us. You're going to write a paper on this next Thursday. But guys, understand that the other place that nuclear fission takes place is inside nuclear weapons. So guys, the question then becomes, how does this work? How do you take a chunk of uranium and turn it into a nuclear power plant or a bomb? Well guys, the answer is this. Please don't try to draw this, just check it out. Guys, the way that this works is you end up with what is called a nuclear chain reaction. Here's how it goes. You take a chunk of uranium. Inside a nuclear bomb, it weighs about 20 kilograms. It's about 50 pounds. And guys, you take a chunk of uranium and you bombard that chunk of uranium with neutrons. How do you shoot neutrons at uranium? Dynamite. They actually surround this thing of uranium with dynamite explosives. They set all this dynamite off that accelerates neutrons at the uranium atoms. Now guys, here's what happens. When a neutron hits a uranium atom, think about an axe splitting a log. The uranium atom splits in half. That's called fission. Guys, what has to happen in order for this uranium to split? What fails? The strong nuclear force. The strong nuclear force fails, energy is released. We end up with two smaller atoms, krypton and barium in this case. But guys, look at what else is released. What are those three things? What's that? More neutrons. And guys, what do those neutrons do? They go and hit other uranium atoms, and they break down, and they release neutrons, and they break down, and they release neutrons. And guys, eventually this runs out of control. The entire bomb of uranium breaks apart, and you end up with a nuclear bomb. Or, if you can control this, you end up with a nuclear power plant. But guys, understand, nuclear power plants are nuclear bombs that are riding on a very tight line between generate electricity and kill lots of people. It's really a scary balance. And I think you know this, right? We've had three. Do you guys know the three places where nuclear power plants have almost turned into bombs? First one was here in the US, 3 Mile Island in Pennsylvania in the 1970s. Then the one that you probably know of happened in Russia. Do you know the name? Chernobyl? Yeah, guys, there are still places in Chernobyl where you can't go today. Interestingly, one of them was the hospital where they brought the workers from Chernobyl when they were trying to save the plant. These people were so radioactive that the room that they put them in to watch them die is still so radioactive that people can't go in there. It's crazy. But then, guys, the third, you better know this one. What was the third time where a power plant almost became a bomb? Japan, Fukushima. Yeah, it was really close. Guys, it was really close. So, again, you'll be writing a paper about whether or not nuclear power generation is a good idea. But, guys, understand that this is what happens in nuclear bombs and happens in nuclear power plants. So, if you understand it conceptually, let me give it to you in animation form. Guys, this is sort of the way this goes down.
Nuclear fission is the splitting of a heavy element's nucleus to form two new elements with smaller nuclei. One of the most important fission reactions is that of uranium-235, which is used in nuclear reactors and atomic weapons. The fission of uranium-235 is initiated when a neutron traveling with enough velocity collides with the uranium-235 nucleus. The collision produces U-236, which immediately splits into two lighter elements, such as krypton-91 and barium-142. The fission event also releases 3 neutrons and energy. The 3 neutrons are capable of initiating more fission events if they encounter a uranium-235 nucleus. If a sufficient or critical mass of uranium-235 is present, the reaction becomes self-sustaining, resulting in the release of a massive amount of energy in the form of heat, light, and ionizing radiation, an atomic explosion.
Get the idea? Yeah, go ahead, Austin.
So they split
Yeah.
How do they contain like all of the energy? You know, like if you did that in like a made a bomb version, how do the nuclear power plants like?
Yeah, how do they contain it? And it's interesting. So, two thoughts. What do they do with the energy in a nuclear power plant? And it's wildly disappointing. Let me go back to this here, and let's talk about it. So, guys, you understand that this nuclear fission process in a power plant we use to generate electricity. Well, how do we do it? And the interesting answer is we take all of this energy that's produced and frankly use it to boil water. And what they do is they take the steam that they make from boiling water using a nuclear bomb, essentially. So they take a nuclear bomb, use it to boil water, take the steam to drive turbines, and that's how they generate electricity. They actually take all of that heat and use it to boil water. So then the question becomes, how do we keep this from becoming a bomb? And it's really interesting. So what is it that causes this thing to become a chain reaction? And the answer is all these neutrons that are released. So what they do to keep this from becoming a nuclear bomb is they insert things that are called control rods. You'll see the picture of them in Bill Nye's video. They're about this tall, they're about this big around, and they're actually made of clay. And what they do is they drop these control rods into the nuclear reactor, and the clay in these control rods actually soak up neutrons. And so guys, every neutron that they can soak up is a neutron that can't go to break down another atom, and they can speed up and slow down the reaction based upon how many control rods they add. The scary part is these control rods also then become radioactive, and we've got to find a place to store them. But that's how they do it. Yeah, go ahead, Kate.
So how are we able to observe like this happening from water sources? How do we figure out that it only releases it?
Yeah, it's fascinating. And frankly, the original idea came from a bunch of math. But then what they've done, and you'll see this not in the video you're going to watch Tuesday, but the video you're going to watch Thursday. Actually, the very first times that they did this, they did it under a football stadium, I think at Princeton. I think it's Princeton. Anyway, somewhere on the East Coast under a football stadium, they built the first nuclear reactor. And the problem that they had wasn't that this was going to turn into a bomb. It's that the neutrons kept shooting out into space, and every neutron that goes into space is a neutron that doesn't keep the reaction going. So the big challenge at first was to contain it. And so what they did is they actually surrounded it in a big box of graphite. Pencil lead, and that graphite actually reflects the neutrons back in. But by doing that, they could count how many atoms have broken apart and how many neutrons have been released, and they were able to figure it out that way. So yeah, you'll see pictures of it. It's really interesting. You guys good on fission? You're good to go? All right, so guys, the next one should be familiar to you. We've got fusion. And guys, this one we've already talked about. Fusion is the process that takes small, good night, I'm hiccuping. Guys, it takes small nuclei and fuses them together. Sounds familiar, right? Where does this take place? The sun. Guys, that's where all the elements other than hydrogen came from. Remember, hydrogen came from the Big Bang. All the other heavier elements came from fusion. Initially in the sun up to iron, and then in supernova after iron. But guys, all elements other than hydrogen came from fusion reactions where small nuclei fuse together to make larger ones. So guys, this process of creating all the atoms that we see today is going on all around us in our sun and other stars. Now guys, what about this? Where on earth does fusion happen here on earth? And the answer is it doesn't. We cannot get fusion to work. We are trying like crazy. There's actually a lab in California that claims that they're really close. But guys, the problem is you've got to put in so much energy to get these atoms to fuse that you don't get out as much energy as you put in, and it just doesn't make sense. We can force it to happen on small scales, but guys, we can't get this to work. So the only place that fusion happens right now on the Earth is in is in hydrogen bombs. You may have heard of hydrogen bombs. They're a whole new flavor of nuclear weapon. Those are actually fusion bombs. They're not fission bombs, they're fusion bombs. But do you guys know how fusion bombs, hydrogen bombs work? They actually detonate a fission bomb, and the fission bomb, the uranium bomb, surrounds the tank of hydrogen, and what they basically do is make a little star. They set off a fission bomb, like a uranium or plutonium bomb, that squishes some hydrogen, causes it to fuse into helium, and that's how hydrogen bombs work, or fusion bombs. But it takes the energy of a fission bomb to get a fusion bomb to go. It's crazy stuff. So guys, what does fusion look like? Well, it kind of looks like this. You don't need to draw this, but it's really fundamentally simple. You got a couple hydrogen atoms. Remember, our sun is mostly hydrogen. And those hydrogen atoms fuse together. They turn into helium. That disrupts the strong nuclear force and energy is given away. It's really surprisingly straightforward. It's just really hard to get to happen. But that's the scoop. So guys, fission and fusion, you good? All right. Time to glove up and start fiddling with the uranium. So guys, we are now done with the high energy nuclear changes. So now it's time, and you want to scratch this in your notes, now it's time to talk about low energy changes. And guys, these low energy changes you've probably heard of because it's called radioactivity. Well guys, what is radioactive decay? Well guys, the term decay simply means to break down. And when we apply that to atoms, the idea is that unstable nuclei, all on their own, just spontaneously decay. And guys, when they decay, the strong nuclear force breaks. But it's not a nuclear weapon. This happens one atom at a time. The strong nuclear force breaks. A radioactive particle shoots out of the nucleus, but it stops there. So this is a low energy process called decay. Now guys, there's three types of decay that you need to know about. And we're going to go over them one at a time. You guys ready to go? Can I switch pages? Is that okay? All right, so guys, type number one is what is called alpha decay. Notice that in parentheses, I've given you the abbreviations for alpha decay. So that kind of squiggly A there on the left is actually the Greek letter alpha. It's lowercase alpha, but it's alpha. But then guys, notice the other way that we represent an alpha particle. It is actually helium 4/2. Guys, it turns out that alpha particles, and I'll show you some in a minute, guys, alpha decay involves the release of a helium nucleus. So guys, you better be able to answer this. What is a helium nucleus made of if we know that helium is 4/2? How many protons are in helium? 2. How many neutrons are in helium? Not 4, 2, because 4 minus 2 is 2. So guys, a helium nucleus is 2 protons and 2 neutrons. And so when an atom goes through alpha decay, it is releasing a helium nuclei. It is releasing 2 protons and 2 neutrons. Now guys, here's the trick. These helium nuclei are big and they are fat and they are slow. So you ready for the $10,000 question? How big and fat and slow are they? Well guys, they are so big and so fat and so slow that Lord Rutherford, Ernest Rutherford, chose alpha particles as the particles to shoot at the gold. Remember that? Because guys, Rutherford figured if alpha particles could get through the gold, anything could get through the gold because alpha particles are so big and fat and slow. So guys, one more thing to write down, and then I'm going to show you some alpha particles. I'm going to give you what is called an ROT. That is a rule of thumb. So guys, you're going to need to know some things about alpha decay. The thing that you need to know, the rule of thumb is this. When something goes through alpha decay, Z, the atomic number goes down by 2, and A, the atomic mass, goes down by 4. All right. You guys all caught up? Let's play with some alpha particles. So guys, in order for this to make sense to you, you need to understand some things. So this is uranium. This is what uranium looks like when we dig it out of the ground. This is not pure uranium. We could not make a bomb out of this. We would have to first purify it in things called centrifuges. For those of you that don't know, this is what we've been accusing Iran of doing for the last decade or so. Ahmadinejad and all of his buddies, we're pretty sure, have centrifuges buried underground that are taking this uranium ore, spinning it around, collecting the uranium in the idea of creating nuclear weapons. Frankly, we can't prove that it's happening, so what did we do instead? Do any of you know? We took down their centrifuges with a computer virus. Did you guys know that? Yeah, the NSA actually released a computer virus into all of their centrifuges and shut them down. Anyway, okay, so guys, this is uranium, but again, this is not uranium that can be turned into a weapon. This, oh, by the way, do you know, I didn't tell you, where did we get this? Moab. Guys, if you've been to Moab, as you're driving south into Moab, right before you cross the river, on the right-hand side of the road, have you noticed that big hillside that they're slowly scraping and taking away and putting in railroad cars? Guys, that used to be a uranium mine. Now we're cleaning it up at the cost of millions of dollars. But guys, this is actually uranium ore that was dug up in Moab. Okay, this is a Geiger counter. You guys familiar with these things? It's a radioactivity detector. Here's the way it works. There's a tube that's inside the back of this detector, and it's actually hooked up to some leads that are then hooked up to a computer. And what happens is anytime a radioactive particle goes through this tube, it creates a little current. And then the computer detects that current and it beeps to let you know that it's been hit. So when I turn this on, you can hear that it's beeping. What causes it to beep? Radioactive particles hitting the tube. Now guys, just listen for a second. Get a sense of this. Kind of awkward, right? So guys, you'll notice that it's beeping. Yeah? What does that mean? Well, it means that we're always being hit by radioactive particles. Where do they come from? The lights, the sun, stars, distant cosmic things, radioactive elements that are all around us. But guys, the bottom line is we are always being hit by some amount of radioactivity. The name for this is background radiation. Now guys, compare that to this. This thing can't even beep fast enough to keep up with all the radioactive particles that are spewing out of this chunk of uranium. Guys, if you could see radioactive particles, you would see them like a shower head just raining out of this in all directions. And as they hit the tube in this Geiger counter, eventually this Geiger counter can't even keep up because it can't beep fast enough to keep up with all the radioactive particles coming out of this thing. You get the idea? So guys, we are going to play with this for the remainder of the day. But guys, as we do, you need to understand that these uranium atoms are going through alpha decay. So some of the particles that are crashing in, that's annoying, some of the particles that are crashing into that Geiger tube are actually alpha particles. Now guys, the question is this: when uranium goes through alpha decay, what does it do to the nucleus of the atom? Well, guys, we're going to answer this, and I'm not going to have you write this down in your notes. Just check this out. But, guys, one of the things that you've got to be able to do is you've got to be able to figure out what does alpha decay do to the nuclei of atoms. And, guys, this is how we're going to represent it. Instead of doing uranium, we're going to do radium. And it goes like this. If a radium atom undergoes alpha decay, what happens to it? Well, guys, radium is element number 88, and it has a mass of 226. And if this undergoes alpha decay, what will happen to it? Well, guys, check this out. Here's the way that this goes. We understand that this is an alpha particle. An alpha particle is a helium nucleus. So if radium undergoes alpha decay, the question is what's left over? Here's how to figure that out. Guys, let's talk about the number of protons and neutrons in radium. How many protons in radium? 88. That's the bottom number. How many neutrons in radium? How do you figure it out? Subtract 226 minus 88, it's 138. Now, guys, check out this. What is an alpha particle made of? What is an alpha particle? How many protons? It's a helium nucleus. How many protons? 2. How many neutrons? 2. So, guys, now let's go over here. If radium starts out with 88 protons, and if it loses 2 protons, how many are left? 86. And if radium starts with 138 neutrons and loses 2, how many are left? 136. So guess what? Radium's not radium anymore. This is no longer element 88. It is now element 86. And element 86 is radon. And now what is its mass? We'll add up 86 and 136, and it's 222. You get the idea? That's alpha decay. Okay. So now, guys, we're ready to move on to beta. Write it down, and then we're going to talk. All right. So, guys, this is kind of disturbing. Check this out. You ready? Here we have background radiation. Not very rapid. Here we have full exposure as the radioactive particles from this uranium are bombarding the Geiger counter. I'll turn this off while you're writing and then check this out. You guys okay? So guys, check this out. Full exposure, going like crazy. Now guys, watch close and listen closer. What happened? Slowed down. Guys, why did the beeping slow down? When did it slow down? Let's do it again. Full exposure. Now it's slower. What's going on? Interference. Say it again, Jessica. What's going on? Yeah, so here's full exposure, right? But when I flip my hand and put my hand in the way, the beeping slows down, which tells you what? Some of this stuff is not getting through my hand. It is actually getting stuck in my hand. So guys, is everything getting stuck in my hand? It's not. So guys, what's going on? Well, it turns out that the alpha particles are so big and fat and slow, they can't even get through my hand. So guys, when I flip my hand over, the alpha particles are stuck. But is something getting through my hand? Absolutely. And guys, what's got to be true of the stuff that's getting through my hand relative to alpha particles? Got to be smaller and faster. And guys, those smaller, faster things are actually called beta particles. So guys, beta particles are smaller and faster than alpha particles. So what are they? Well, guys, the answer is this, and this is crazy. A beta particle is an electron that comes out of the nucleus when a neutron becomes a proton. I am not making this stuff up. Guys, a beta particle is an electron that comes out of the nucleus when a neutron becomes a proton. And guys, what do we know about these beta particles? Well, we know that they're small and they're fast and they're high energy. But guys, this seriously happens. Inside those uranium nuclei, there are neutrons that are just hanging out doing their neutron thing, and all of a sudden, bink, and a neutron turns into a proton, and an electron goes flying out of the nucleus. Now guys, how many electrons are in the nucleus? None. Where are the electrons? Moving around the nucleus. But guys, inside these nuclei, neutrons can magically turn into protons, and when they do, an electron comes flying out of there that wasn't even there in the first place. And this happens all the time. So guys, what does that do to the nucleus? Well, here is your rule of thumb. Guys, the rule of thumb is Z goes up by 1 and A does not change. So guys, let me show you what that means. Again, you don't need to write this down, but you will be doing this in homework, so let me show you. So guys, it goes like this. We're not going to look at uranium, let's look at iodine. So the question is, what happens to iodine 127 when it goes through beta decay? So this is iodine 127, and the question that we're asking is, what happens when it goes through beta decay? And notice, guys, how we represent a beta particle. It is an electron, but we put the -1 first rather than second, so it doesn't look like a normal electron. But now let's look at their nuclei. So guys, how many protons in iodine? How many protons in iodine? 53. How many neutrons? Subtract 74. Now, guys, what is a beta particle? How many protons and neutrons? None. What is it? It's an electron. But guys, what happens when this takes place? So guys, when it goes through this process, what happens to one of these neutrons? It turns into a proton. So we end up with 54 protons. But now how many neutrons do we have? 73, because one of them turned into a proton. So guys, this is no longer element 53, it's now element 54. So element 54 is xenon. But what is the mass? Well, 54 plus 73 is still 127. So guys, look at what happened. The atomic number went up by 1 and the mass stayed the same. That is your rule of thumb. The atomic number goes up by 1 and the mass stays the same. You get the idea? All right, one more to go. Ready? Here's how this goes. So guys, full exposure. Now what's missing? Full exposure, now what's missing? Alpha particles, where are they? In my hand. What's going through my hand? Beta particles, why are they going through my hand? They're smaller and faster. But the question then becomes, can we block the beta particles? The answer is yes, with lead. Guys, this is a lead sheet. This is why they drape you in lead when you get an X-ray, because they want to protect your body from the stuff that they don't want to irradiate. So guys, it goes like this. Full exposure. Now what are we missing? Alpha. Remember background. Full exposure minus alpha. Ready? Now we're minus beta. Where are the beta particles? In the lead. But is something still getting through? Yeah. And what has to be true of the something that's getting through? It's got to be even smaller and even faster. So how small and fast is it? It is so small and so fast that it doesn't even exist. This is what is called gamma radiation. And guys, gamma radiation doesn't even exist. It is not a particle. Gamma radiation, guys, is simply high energy waves, very, very similar to light. By the way, guys, this is the stuff that kills you. The gamma rays are so high energy that they can actually interact with the DNA of your body and cause disruption and cancer. But guys, you got to understand, because this isn't a particle, it doesn't change the atomic number or the atomic mass. It is simply a release of energy. Okay, so guys, what do you need to be able to do with all of this? Well, you need to understand fission, fusion, alpha, beta, and gamma decay. But guys, there's another thing that you've got to be able to do. This is in your homework. Please don't try to write this down, but let me show you part of what your homework is going to look like. Guys, it's going to look like this. These are these decay equations that I showed you previously. And guys, just watch and do this with me, and I think you'll get it. Your goal is going to be to identify the type of radiation and then the particle that fills in the blank. So guys, when you fill this in, what are the types of radiation that you're going to run into? Well, alpha or beta, why not gamma? It doesn't change the nucleus of the atom. We only do these for alpha and beta, so you only got to keep track of two things. So guys, you do this by comparison. So check out what happens. We start with this and end up with this. But look at what happens to the atomic number. The atomic number goes up by 1 and the mass stays the same. Is that alpha or beta decay? Beta. So you write down beta. And then guys, how do we represent a beta particle? Like this, E-1. Now guys, check out this. We start with polonium-84, and that goes down to lead-82. Then the atomic number goes from 209 to 205. Is that alpha or beta? Alpha, and we represent an alpha particle like this. But guys, notice we can also do this the other way. We start with uranium-238. What's this? Alpha or beta particle? That's an alpha particle. So guys, what does that do to the atom? Well, the atomic number is going to go down to 90, and the atomic mass is going to go down to 234. And so guys, the product of this will be thorium, element number 90, 234. You got the idea? Okay, so guys, grab your homework. So guys, allow me for a moment to speak to you from experience. This is a homework assignment number 2. Notice that it's double-sided. Guys, this is a lot of homework. Here's the deal. You guys have your test on the 19th, right? I know there's a fair number of you that are very, very concerned about your first quarter grade in this class. You want to do well on this last test. Guys, speaking from experience, how well you do on this last test is going to largely be determined by how well you do on this homework. When people do poorly on this test, it's typically because they didn't spend the time they needed to do well on this. Guys, this is a lot of homework, but realize you have a long time to do it. This for you is not due until what, next Thursday? When do I see you again? You guys know, is it Friday? What's A day? Thursday. Guys, this will be due next Thursday. You have 6 days to do this. But guys, do it well. Of course, unless you don't want to do well on the test, and then that's up to you. But guys, spend the time that it takes to do well on this. We have, gosh, only like 5 minutes left. But guys, do well on this homework. Enjoy your time with the sub. Spend some time to do well on the papers that you're writing. Oh, and guys, by the way, the sub won't know the answer to this. Let me just tell you, I know this is always your first question. The papers that you're going to be writing in response to the day on Tuesday, there's actually 2 separate papers. Don't put them together. You'll write one paper for Bill Nye, another paper for Nova Science Now. But guys, they don't have to be huge. If you're writing more than a page for either one of these, you're probably saying too much. Answer the questions in well-crafted sentences and paragraphs, but guys, don't get crazy on this. Have a good weekend. Have a good week. Think fun.